Welcome to CERN and welcome to the Hadron Cafe today. On the menu today, not a dish you should try at home, a recipe for the universe with Professor Alvaro de Rujula. Professor.
Good morning. I thought you were going to ask me some questions for starters, but if you don't, I will answer them anyway. The title of this session is The Recipe for the Universe. And the question is, if you had to make a universe in your own kitchen, because you had nothing better to do, what ingredients would you need? Now, it turns out that our universe is a very surprising place, because we are made of a certain type of matter, and most of the universe is made of something else. So that the stuff of which we are made, and the planet is made, and the atmosphere is made, and the sun is made, and all the stars are made, adds up to only 4% of the stuff of the universe. So we are we're not in the center of the universe, we are not even made of what the universe is mainly made of. The universe is made of 5 times more of something that we call dark matter, which we have no idea what it is, but we know it's there because we can see its effects. An ensemble of stars like a galaxy would not stick together the way it does if there wasn't more matter to it than what we see. And that extra matter, which is probably composed of some mysterious particles that we have never seen, we know it's there and we don't know what it is. And there is about 5 times more of that than ordinary matter, such as us in the universe. So one of the things we're doing at the LHC is to try and produce particles that could be what we call candidates to be the dark mass of the universe. Since there is something out there that we don't know, we try to make it. That's one of our main aims at the LHC. And I'm talking too long. Why don't you intervene and do something?
Well, what's going to happen in a little while is we'll have a demonstration of some hands-on physics by Physica Express over there. We get to hear the sonnets again, lucky us. And we'll also be taking questions from Professor Alvaro as well. Professor Alvaro, I have one question for you, and that is the Large Hadron Collider is looking to look at the universe as it might have been shortly after it came into existence. Is it theoretically possible that one day we'll be able to create a universe in much the same way as we're creating the conditions shortly after the beginning of the universe?
Presumably that would take at least all of the energy of the universe, which is not at our disposal. Also, the laws of nature at the moment of creation of the universe, we don't know them. We'll presumably never know them experimentally. So I cannot answer your question either yes or no, but I think it's quite unlikely that you manage to make a universe yourself if you are bored this evening.
Okay. Well, we might now turn to Physica Express and ask them to show some demonstrations.
Okay. Hi, this is Carlo and I am Eva, and we're from Croatia to show you some interesting experiments. Basically, it's things relating to pressure. And what we have here is 2 cans which, with a little bit of water inside them, and we heat it up, and the water started to turn to gas. So what we're going to do is take that can and put it in a bowl of water, and the can will implode. So we can repeat it one more time. Okay. So why is this? When we turn water into a gas, it had very large pressure. So we have a large pressure inside this container. And when we flip it out and put it in cold water, that pressure suddenly drops and becomes much less. And you have this force that actually implodes the can. And this is something you can do at home if you want to. So next thing relating to power of pressure, we have our own homemade vacuum bazooka, which is down there. You can probably see it on the monitor. And the reason it's called bazooka, well, it's supposed to do what bazooka does. Okay, but just one moment. Okay, what we're doing, we're pumping out the air from this tube. and we're creating vacuum inside this tube. And what should happen, if we don't have any technical problems, the cork on one side, oh, okay, hope you all see that. So the cork, we're pumping out the air inside this tube. And on one side you have a cork, and on the other side you have a piece of something. It doesn't actually really matter what it is. At some point, this cork passes through this hole. Okay? And the pressure up here is bigger than the pressure inside this tube. And it pushes that cork to fly out. And it acts like bazooka. Okay? One more thing. We have here a vacuum pump and just a vacuum chamber. And we're going to put a balloon inside that vacuum chamber and pump out the air. Okay? And what will happen, as you may see, and over there, balloon starts to grow. So all we are doing is making a vacuum inside this vacuum chamber. And we're releasing the pressure inside this chamber. And the pressure inside the balloon is greater than the pressure inside this vacuum chamber, and that pressure pushes the balloon to expand. And if we turn off our vacuum pump and let the air come in, the balloon will shrink.
Thank you very much. Physica Express, all the way from Croatia. I believe it's now time for another number from the CERNets. And the CERNets are not brought in especially for the day. They, in fact, work here, I understand, during the day. And at night, well, I think we can guess.
They sing.
They sing.
What I feel when you're here, what I sense when you're near is an energy field, a pervasive, strong yield. If you turn me away, I will slowly decay like a lost cosmic ray that fell out of its way, 'cause I love every proton of you. You're so sweet, you're so nice, you're so sugar and spice. You're an energy field, a pervasive, strong yield. You give love, you give dreams, you give mass to my bones. You're all over the place, you fill each empty space, and I love every proton of you. You spin around unconfined with emotion. You make my universe blue. Yes, you do, yes, you do. I feel this strong force that's pulling my motion, hopelessly pulling me to you. If you turn me away, I will slowly decay like a lost cosmic ray that fell out of its way, 'cause I love every proton of you. strong yield, and I love every proton of you. Every proton. Yes, I love every proton of you. Every proton. Yes, I love every proton of you. Every proton of you. I love your protons.
Thanks very much to the CERNets. Obviously, a multi-talented bunch of people here at CERN. It's now time for questions. If you have any questions for Professor Alvaro de Rujula, he is. What is your field of speciality, Professor?
I'm a theoretical physicist.
There you go. Any questions on theoretical physics today? He'd be happy to answer them for you. There's a microphone out there somewhere, I understand. Any questions out there today? Yes, we have one at the back, I believe.
Questions don't have to be on theoretical physics.
No. They could be just about the running and operations of CERN. It's a very big operation. How many people involved in getting this project together, Professor Alvaro? Do you know?
There are about 2,300 people working at CERN. Then there are about 7,000 so-called users, people who come here and profit from the facilities that we have, mainly the accelerator. But very much of what we do here is done by people from outside, from universities all over the world. We have about 70 nationalities represented at CERN. So if you go to the cafeteria, most of the time you won't understand anything of what people are talking.
It's because they're talking physics. One of the things I'm aware of is that the project itself, the machine that you've made, which is a very large one, it too has a multinational flavour or character.
Yes, CERN is an organization which has always constituted of very many countries. There are 20 countries from Europe that participate in the organization. It's probably the first, and not only the first, but the only international organization that works properly. We scarcely ever fight. We are all very happy to be here, and it works very nicely. We give an example of the fact that humans from all over the world can work together in a constructive fashion. And that, I think, as an impact in society, it's perhaps the strongest we have. We are an example of excellent worldwide organization.
And the machine itself has roots from everywhere. I believe there are parts from Pakistan, parts from Russia, parts from Portugal, parts from pretty much everywhere.
Yes, we have Russian steel and Italian electronics and so on and on and on and on. We have pieces of this thing come from everywhere in the world.
Now, Professor, you've been involved with the project for how long? How many years?
I'm actually not directly involved in the project because I'm a theoretical physicist. I'm that kind of people who try to understand things but actually don't do them. Let the others, who are called experimentalists, actually build the machines that we think are necessary to progress in our understanding of nature, which is what we want to do, understand nature.
I have a question for you, Professor. Given our current understanding of the universe, how is it going to end?
Oh, the future is very bleak because the universe is expanding in an accelerated fashion. So all the distant galaxies that we now see will one day become invisible, and we will only see our own little group of galaxies. So there will be a future about, 100 billion years from now, where astronomers will have nothing to do because they can only see the neighborhood and nothing truly interesting and far away. That's not the first thing that's going to happen to us. In a few billion years, the sun will become a red giant star and increase in size till it reaches the Earth. So we will be cooked sooner or later. Probably we're going to destroy ourselves much more efficiently than before, but if we happen to last for another billion years, we will have to move to another planetary system.
You, sir.
Considering what we know now and what you expect to learn in the near future, how much of this was Einstein aware of?
Einstein was aware of much of the basics, because everything we do is based in practice on the theory of relativity that he invented. However, at the time of Einstein, very few of the forces of nature were known, only gravity and electromagnetism. We know now that there are two other forces, which are called the strong force and the weak force, not very intelligent names. And so he didn't have the elements to know everything we know now. And in the last 70 years or so, we have had a tremendous development of our understanding of things that Einstein couldn't suspect because they were not known at the time. So let me say that he knew half of it.
Do we have any more questions? Yes, we do. We have a question over here. My Croatian friends.
Can you build a black hole here in the CERN?
This is a question that will require more time than I have, and there is a special session at 6 p.m., if you have the patience, which will no doubt be mainly dedicated to that. There has been a lot of noise in the press that we may fabricate something that will destroy the world. Now, we take this very seriously, not because it is serious, but because it frightens people. And we know that that is not possible. And when we say we know, we mean we know. And there are things in science that you know. Let me give you an example of something that you know. You know that space has 3 dimensions. Because if you want to instruct your neighbor, your friend, to go to the neighbor's farmer yard and steal an apple from a tree, you have to give your thief 3 pieces of information. How far to move this way, how far to move this way, and how much to climb in the tree. There are 3 pieces of information. Those are the 3 dimensions of space. And this is an absolute truth. It is not disputable. If you take someone in a jungle in somewhere in Brazil who has never had any contact with us, and who is instructing someone else to steal a fruit from the neighboring tribe, this other guy will also need 3 pieces of information and conclude that there are 3 dimensions of space. So there are 3 dimensions of space. That's one thing we know, we all know, it is true. On the same type of level of truthness, that is to say, based on things on which we all can agree because we have observed them, we can prove that if we were to make something that would destroy the planet, that something has been made naturally in the universe billions and billions of times by the interactions of something that are called cosmic rays, which are particles that have a tremendously high energy, much bigger than what we can make, that hit the top of the atmosphere and would produce these things that would destroy us. If you don't believe that there are accelerators in space that make cosmic rays of very high energy, you can go to the little museum that we have on the other side of the street, whose name now escapes me, Microcosm, and see there the particles that are coming from the top of the atmosphere, made by these very high energy particles. So there are very much higher energy particles in the universe than the ones we can make. Those would have made collisions that would have destroyed stars and would have destroyed the moon, would have destroyed the planets, and even our planet. So it hasn't happened, and it has had zillions of chances to happen. So it's not going to happen this time. And the basis for this statement that I'm making is science that we know and we have studied and understood, and on which everyone studying and understanding it would agree. So when we say that there is no danger, we mean that there is no danger. It's based on things on which we can agree. We know there is no danger. However, since there is such a fashion discussing this subject, we have to discuss it. It's sort of fun, but it's a waste of time.
And there will be another discussion on this at 6 p.m. this evening. Well, that's all we have time for today. Thank you very much for your attendance. Thanks very much to Professor Alvaro de Rujula for his help today. On the way out, you'll exit through this door behind me here. Thank you.